morning. Today we'll study about temperature stresses. So far we have studied about normal stresses, tensile stresses, compressive stresses, etc. Now we will deal with temperature stresses. This is the beginning of module 2. Now what is the importance of studying this temperature stresses? Now you have seen expansion joints provided in railway lines. Why it is provided? Because whenever materials are subjected to increase in temperature, there will be increase in length, and when there is decrease in temperature, there will be decrease in length. So in order to account for this increase in length and decrease in length, we will provide some joints so that when the temperature increases, if the length increases, there is some space for the material to take this place when there is some expansion. That is why we are providing expansion joints in railway lines, and you can also see some cracks on the compound walls if we are not providing expansion joints for larger length. So it is a must that we must provide expansion joints at a particular distance in order to prevent the cracking of material due to the development of temperature stresses. Okay. So we should have an idea what is the gap or expansion joint that has to be provided in different materials to account for the temperature stresses developed. So that is the importance of studying temperature stresses. So every material expands when temperature rises and contracts when temperature falls. Okay. So the change in length due to change in temperature is found to be directly proportional to the length of the member. For example, if you have a small bar like this, we are increasing the temperature to T degrees Celsius. The change in length, that is due to the increase in temperature, there may be some increase in length of the bar, and we can write this change in length delta L is directly proportional to the increase in temperature. For example, if you are increasing the temperature from 23 degrees Celsius to 33 degrees Celsius, then what is T? T will be equal to 10 degrees Celsius. That is the rise in temperature. And it is also proportional to the length of the member. Okay, so if the length is more, then increase in length will also be more. If the rise in temperature is more, then the increase in length will also be more. So we can write delta L, the change in length, is equal to let us write the constant of proportionality as alpha into T into L. Okay, where alpha is known as coefficient of thermal expansion. It is the constant which depends on the material. So it is different for different materials, and its value, for example, for steel, the value of alpha is equal to, alpha for steel is equal to 12 into 10 raised to minus 6 per degree Celsius. So how can you define coefficient of thermal expansion? It is the change in unit length of the material due to unit change in temperature. Okay, so the constant of proportionality is called alpha. That is, the change in length due to change in temperature is directly proportional to the length of the member and also to the change in temperature. It is directly proportional to the length of the member and also directly proportional to the change in temperature. So you can write delta L equal to alpha into T into L. Alpha is the coefficient of thermal expansion. It is different for different materials, and for steel it is 12 into 10 raised to minus 6 per degree Celsius. This value will be given in the question. So you can say delta L is equal to alpha into T into L. Okay. Okay, now we'll study about temperature stresses. So you consider that the change due to temperature is not prevented. That is, the changes due to temperature are permitted freely. What will happen? Change due to temperature is permitted freely. That is, if a member is subjected to an increase in temperature or decrease in temperature, and if it is allowed freely to expand or contract, what will happen? So for example, you consider this bar. Let L be the length of this bar, and we are increasing the temperature by T degrees Celsius. Let this material be made up of steel. So as a result of this increase in temperature, what will happen? This will expand, isn't it? So since it is not prevented in expansion, we can write that the total change in length delta L is equal to alpha into T into L. And it is not prevented from increasing the length, so it increases the length, and there is no development of temperature stress. No development of temperature stress. So in this case, if we are allowing it to expand freely, no development of temperature stress. There will be no stress developed in the member due to the increase in temperature. Okay. Now next we'll consider if the expansion is fully prevented. That is, you have a member like this, let L be the length of the member. We are preventing the increase in length in this direction by providing a fixed support here. As a result, what will happen? The change in length there will not be any change in length. Why there is no change in length? It is prevented by this force in this support. It is prevented by the force in this support. So actually, if we are not providing any support here, it would have been expanded to delta L, then that will be equal to alpha into T into L. So if the free expansion is prevented fully, there will be development of some stresses in the member. Okay. Now you consider the bar shown in figure. If the bar is free to extend when temperature increased by T degrees Celsius, its expansion is known as free expansion, and it would have been equal to alpha into T into L. But this extension is completely prevented in this case by the forces developed by this supports. Okay. So this support force P is such that it causes a shortening delta L, which is equal to alpha into T into L of this bar. Okay, that is, this support is preventing the expansion, that is due to the force exerted by this support P. There is a shortening of this much length, even though there is increase in length. Even though there is increase in length, there is a shortening of alpha into T into L length due to P. So we can write, if P was the force, what would have been the change in length? You can write it is equal to PL divided by, you can write it as PL by AE would have been the change in length, where P is the force exerted by the support, L is the length of the bar, A is the area of cross section, and E is Young's modulus of elasticity. This is equal to alpha into T into L, or this L and L cancels, L and L cancels, this one and this one cancels, and this becomes P into L is equal to P into L by, you can write P into L by A is equal to alpha into T into capital E, or P by A you can write sigma sigma into L and L cancels. So here there is no L. P by A you can write it as sigma, where this sigma is known as the temperature stress. P by A is equal to alpha into T into E. That is temperature stress sigma is equal to alpha into T into E. Okay. So you can write temperature stress sigma is equal to alpha into T into E. So temperature stress is equal to coefficient of thermal expansion into increase in temperature or change in temperature into modulus of elasticity. So this is the value for temperature stresses. So if we are preventing the expansion due to increase in temperature completely, then there will be development of temperature stresses, and that temperature stress will be equal to alpha into T into E. Okay. And here you can see there is a decrease in length. This much length is not allowed to expand. So this temperature stress is compressive in nature. Temperature stress is compressive in nature because it is preventing the increase in length of this bar, which is equal to alpha into T into L. So this temperature stress here is compressive in nature. This is compressive in nature. Okay, now we'll see if what will happen if free expansion is prevented partially. If free expansion is prevented partially, as in the case of this member, you can see here free expansion is prevented partially. That is, we are providing a support in between this complete expansion. That is, we are providing a fixed support here. So if the free expansion is prevented partially, as in case of the member shown in figure, the force developed correspond to the amount of free expansion prevented. The force developed P correspond to the amount of free expansion prevented. Okay. So we'll see how to find out the temperature stress developed. Okay. Now here you can see this was the actual expansion, but this much expansion is prevented. This much expansion is prevented. Okay. So you can write the shortening caused by the support reaction. The shortening caused by the support reaction delta L is equal to alpha into T into L minus delta. Okay, let this be the delta actual delta happening, expansion happening, and this much is the prevented expansion. So the prevented expansion delta L is equal to alpha into T into L minus capital delta. So what is preventing this much? This is prevented by the force provided by the support reaction, that is PL by AE is equal to alpha into T into L minus delta. Okay, so from which we can find out what is the shortening caused by the support reaction P. Delta L is equal to alpha into T into L minus delta. So from which you can write PL by AE is equal to alpha into T into L minus delta. Okay, here if you have not provided an intermediate support here, this will expand to alpha into T into L, but we are providing a force here by providing a support in between here, and as a result this much expansion is prevented. So this much expansion is prevented by the force provided by the support reaction. So the contraction reduction in length delta L is equal to alpha into T into L minus delta, and this contraction is produced due to this force of the support reaction. So we can write PL by AE equal to delta L, which is equal to alpha into T into L minus delta. So we have studied what is temperature stress and how it is developed if we are providing fully preventing and partially preventing. Okay, thank you.